When considering demand factors for warehouse lighting loads, several aspects require careful evaluation. Firstly, the type of lighting system plays a crucial role. Demand factors are commonly used for systems with numerous individual light sources, such as fluorescent or light-emitting diode fixtures. However, in warehouses, high bay fixtures with metal halide lamps might be present, exhibiting a more consistent load profile. Secondly, usage patterns significantly influence demand. Table 220.42 is structured around typical usage patterns across various occupancies. Warehouses often have lights operating for extended durations, although some areas might experience less frequent use. Thirdly, the size of the space is a determining factor. The 50% demand factor in Table 220.42 is intended for large spaces exceeding 12,500 volt amps. Smaller warehouses may require a higher demand factor. Fourthly, code requirements must be adhered to. The National Electrical Code does not specify a particular demand factor for warehouse lighting. It mandates that the electrical system be designed to accommodate the maximum anticipated load. With these considerations in mind, certain recommendations can be made. It might be appropriate to consider a high demand factor for warehouses where lights are on for long periods or where the space is expansive. Exercise caution when applying a very low demand factor. A 0% demand factor essentially assumes that all lights will operate simultaneously, which is improbable in a warehouse. If uncertainty exists, consult with local electrical authorities to ascertain the appropriate demand factor for the specific warehouse design. Regarding the Stallcup's electrical design book, the approach of not applying a demand factor to lighting load, except for continuous lighting, might be reasonable for warehouses with a relatively small number of fixtures or where lights are not on for extended periods. However, for larger warehouses or those with high bay fixtures, a more conservative approach with a high demand factor may be warranted. To delve deeper into the calculation of lighting loads and the application of demand factors, firstly, understand the basic lighting load calculation. This involves determining the total voltamps of lighting required for a specific area. This is often calculated based on the area square footage and the occupancy type as outlined in the National Electrical Code Table 220.12. For example, a warehouse might have a requirement of 0.25 voltamps per square foot. So, a 10,000 square foot warehouse would have a calculated lighting load of 2,500 voltamps before applying any demand factors. Secondly, continuous versus non-continuous loads are essential. The National Electrical Code defines a continuous load as one where the maximum current is expected to continue for 3 IOs or more. For continuous loads, the overcurrent protection device and conductors must be rated for 125% of the continuous load. This means that if the lighting load is considered continuous, the calculated load must be multiplied by 1.25 to account for the additional stress in the electrical system. Thirdly, demand factors from Table 220.42 are applied. Table 220.42 of the National Electrical Code provides demand factors for various types of occupancies. For warehouses, the demand factor is typically 100% for the first 12,500 voltamps and 50% for the remainder. This means that for a larger warehouse with a lighting load exceeding 12,500 volt amps, you would only need to account for half of the load above this threshold. Fourthly, consider specific area usage within the warehouse. Not all areas of a warehouse are used uniformly. Some areas may have lights on constantly, while others are only used occasionally. In such cases, it may be appropriate to divide the warehouse into different zones and apply different demand factors to each zone based on its usage pattern. For example, if 2,000 square feet of the 10,000 square foot warehouse is used for office space, the lighting load for this area might be calculated separately using the demand factors for office spaces, which could be different from those for the warehouse storage area. Fifthly, high bay lighting systems should be taken into account. High bay lighting systems, commonly used in warehouses, often utilize high-intensity discharge lamps such as metal halide or high-pressure sodium. These lamps have different operating characteristics compared to fluorescent or light-emitting diode fixtures. They may have a higher initial inrush current and a longer strike time, which can affect the overall demand in the electrical system. It's crucial to consider these factors when determining the appropriate demand factor. Sixthly, energy-efficient lighting upgrades may affect the demand. If the warehouse has recently upgraded to more energy-efficient lighting, such as light-emitting diode fixtures, the actual lighting load may be significantly lower than what is indicated in the original electrical design. In such cases, it may be appropriate to recalculate the lighting load based on the actual power consumption of the new fixtures and adjust the demand factor accordingly. Seventhly, the local amendments and interpretations should be verified. Local jurisdictions may have amendments to the National Electrical Code or specific interpretations regarding the application of demand factors for warehouse lighting. It's essential to check with the local electrical inspector or authority having jurisdiction to ensure compliance with all applicable requirements. Eighthly, document your assumptions and calculations should be done clearly. It is important to document all assumptions and calculations used in determining the lighting load and demand factors. This documentation should include the square footage of the warehouse, the lighting load per square foot, the type of lighting fixtures used, the usage patterns of different areas, and any applicable demand factors. This documentation can be helpful in justifying the design to the electrical inspector and in troubleshooting any issues that may arise in the future. Ninthly, consider future expansion. When designing the electrical system for a warehouse, it's important to consider the possibility of future expansion. If the warehouse is likely to be expanded in the future, it may be prudent to design the electrical system with sufficient capacity to accommodate the additional lighting load. This could involve using a higher demand factor or installing additional electrical panels and circuits. Tenthly, the voltage drop calculations are important. In addition to calculating the lighting load and demand factors, it's also important to perform voltage drop calculations to ensure that the voltage at the lighting fixtures is within acceptable limits. Excessive voltage drop can cause the lights to dim or flicker, which can be annoying and potentially hazardous. The National Electrical Code provides guidelines for voltage drop in branch circuits and feeders. To calculate the lighting load for a warehouse effectively, firstly, measure the square footage accurately. Start by accurately measuring the total square footage of the warehouse space, including all the areas that require lighting. This will serve as the basis for calculating the initial lighting load before applying any demand factors. Secondly, determine the volt-amps per square foot requirement. Consult National Electrical Code Table 220.12 to determine the volt-amps per square foot requirement for warehouse spaces. This value depends on the type of occupancy and the level of illumination required. For example, a typical warehouse might have a requirement of 0.25 volt-amps per square foot. Thirdly, calculate the initial lighting load. Multiply the total square footage of the warehouse by the volt-amps per square foot requirement to calculate the initial lighting load. For instance, if the warehouse is 10,000 square feet and the requirement is 0.25 volt-amps per square foot, the initial lighting load would be 2500 volt-amps. Fourthly, identify continuous lighting loads. Determine whether any of the lighting loads are considered continuous, meaning they are expected to operate for 3 hours or more at a time. If so, these loads must be multiplied by 1.25 to account for the additional stress on the electrical system. Fifthly, apply demand factors from Table 220.42. Consult National Electrical Code Table 220.42 to find the applicable demand factors for warehouse lighting. Typically, the demand factor is 100% for the first 12,500 volt-amps and 50% for the remainder. Sixthly, calculate the adjusted lighting load. Apply the demand factors to the initial lighting load to calculate the adjusted lighting load. For example, if the initial lighting load is 20,000 volt-amps, the adjusted lighting load would be 12,500 volt-amps multiplied by 100% plus 7,500 volt-amps multiplied by 50%, which equals 16,250 volt-amps. Seventhly, consider specific area usage patterns. Evaluate the usage patterns of different areas within the warehouse. If some areas are used less frequently or have lower lighting requirements, you may be able to apply additional demand factors or reduce the lighting load accordingly. Eighthly, account for high bay lighting systems. If the warehouse uses high bay lighting systems, such as metal halide or high-pressure sodium lamps, consider their unique operating characteristics such as higher inrush currents and longer strike times. Adjust the lighting load or demand factors as necessary to account for these factors. Ninthly, verify compliance with local codes and regulations. Check with a local electrical inspector or authority having jurisdiction to ensure compliance with all applicable codes and regulations regarding warehouse lighting loads and demand factors. Tenthly, document all assumptions and calculations. Document all assumptions and calculations used in determining the lighting load and demand factors. This documentation will be helpful in justifying the design to the electrical inspector and in troubleshooting any issues that may arise in the future. When it comes to factors influencing the choice of demand factors, firstly, occupancy type is a critical consideration. Different occupancies have different lighting needs and usage patterns. For example, an office building will typically have higher lighting requirements and more consistent usage patterns compared to a warehouse. Therefore, the demand factors for office buildings will generally be higher than those for warehouses. Secondly, the size of the facility matters. Larger facilities tend to have more diverse lighting loads and usage patterns compared to smaller facilities. As a result, demand factors may vary depending on the size of the facility. For instance, a large warehouse may have lower demand factors compared to a small retail store. Thirdly, the type of lighting system used needs assessment. The type of lighting system used can also affect demand factors. Energy-efficient lighting systems, such as light-emitting diode or fluorescent fixtures, typically have lower power consumption compared to traditional incandescent or high-intensity discharge lamps. Therefore, demand factors may be adjusted to reflect the lower power consumption of energy-efficient lighting systems. Fourthly, lighting control strategies play a part. The use of lighting control strategies, such as occupancy sensors, dimming systems, and daylight harvesting, can significantly reduce lighting energy consumption. Demand factors may be adjusted to account for the energy savings achieved through these control strategies. Fifthly, usage patterns need assessment. The way space is used can also impact demand factors. For example, a warehouse that operates 24 hours a day, 7 days a week will have higher lighting usage compared to a warehouse that only operates during regular business hours. Demand factors should be adjusted to reflect these different usage patterns. Sixthly, the diversity of loads should be considered. The diversity of loads refers to the extent to which different lighting loads are used simultaneously. If all of the lighting loads in a facility are used at the same time, the demand factor will be higher. However, if the lighting loads are used at different times, the demand factor can be reduced. Seventhly, local codes and standards matter. Local codes and standards may specify minimum or maximum demand factors for different types of occupancies. It is important to comply with these codes and standards when selecting demand factors. Eighthly, historical data and monitoring helps. Analyzing historical data on lighting energy consumption can provide valuable insights into actual demand patterns. This data can be used to refine demand factors and improve the accuracy of load calculations. Monitoring lighting energy consumption in real time can also help to identify opportunities for energy savings. Ninthly, manufacturer's specifications must be considered. The manufacturer's specifications for lighting equipment can provide information on power consumption, operating characteristics, and recommended demand factors. It is important to review this information when selecting demand factors. Tenthly, the professional judgment should be sought. Selecting appropriate demand factors often requires professional judgment and experience. Consulting with a qualified electrical engineer or lighting designer can help to ensure the demand factors are selected appropriately and that the electrical system is designed to meet the actual lighting needs of the facility. To elaborate on the application of demand factors in warehouse lighting and the National Electrical Code considerations, firstly, the general lighting load is determined. The National Electrical Code requires that the general lighting load for a warehouse be calculated based on the square footage of the building and the volt-amps per square foot requirement specified in Table 220.12. The volt-amps per square foot requirement varies depending on the type of occupancy and the level of illumination required. Secondly, demand factors from Table 220.42 are applied next. Once the general lighting load has been determined, the National Electrical Code allows for the application of demand factors to reduce the calculated load. Table 220.42 provides demand factors for various types of occupancies, including warehouses. The demand factor for warehouses is typically 100% for the first 12,500 volt amps and 50% for the remainder. Thirdly, continuous loads are separately accounted for. The National Electrical Code defines a continuous load as one where the maximum current is expected to continue for 3 hours or more. For continuous lighting loads, the overcurrent protection device and conductors must be rated for 125% of the continuous load. Fourthly, energy-efficient lighting is considered as well. The National Electrical Code allows for adjustments to the lighting load to account for energy-efficient lighting systems such as light-emitting diode or fluorescent fixtures. These adjustments can reduce the calculated load and the size of the electrical system. Fifthly, lighting control systems can change the load calculation. The National Electrical Code also allows for adjustments to the lighting load to account for lighting control systems such as occupancy sensors and dimming systems. These adjustments can further reduce the calculated load and the size of the electrical system. Sixthly, emergency lighting systems are excluded from demand factors. The National Electrical Code requires that emergency lighting systems be designed to operate independently of the general lighting system. Therefore, emergency lighting loads are not subject to demand factors. Seventhly, voltage drop calculations are required. The National Electrical Code requires that voltage drop calculations be performed to ensure that the voltage at the lighting fixtures is within acceptable limits. Excessive voltage drop can cause the lights to dim or flicker, which can be annoying and potentially hazardous. Eighthly, conductor sizing is important. The National Electrical Code provides requirements for conductor sizing to ensure that the conductors are capable of carrying the calculated load. The conductor size must be sufficient to handle the maximum current that is expected to flow through the conductors. Ninthly, overcurrent protection is essential. The National Electrical Code requires that overcurrent protection devices, such as circuit breakers and fuses, be installed to protect the conductors and equipment from overloads and short circuits. The overcurrent protection device must be sized to protect the conductors and equipment based on the calculated load. Tenthly, local codes and amendments must be followed. Local codes and amendments may have additional requirements for warehouse lighting systems. It is important to check with the local electrical inspector or authority having jurisdiction to ensure compliance with all applicable codes and regulations. For a clearer understanding of adjusting demand factors for specific warehouse scenarios, firstly consider extended operating hours. If the warehouse operates for extended hours, such as 24 hours a day, 7 days a week, the lighting load will be higher compared to a warehouse that only operates during regular business hours. In this scenario, it may be appropriate to increase the demand factor to account for the higher lighting usage. Secondly, variable occupancy levels matter. If the warehouse has variable occupancy levels, such as periods of high activity followed by periods of low activity, the lighting load will fluctuate accordingly. In this scenario, it may be appropriate to use a demand factor that reflects the average occupancy level over a given period. Thirdly, zoning and control systems play a role. If the warehouse is divided into zones with separate lighting control systems, the lighting load can be optimized for each zone based on its specific usage patterns. In this scenario, it may be appropriate to use different demand factors for each zone to reflect the different lighting loads. Fourthly, automated storage and retrieval systems should be considered. Warehouses with automated storage and retrieval systems may have different lighting needs compared to warehouses with manual storage and retrieval systems. In this scenario, it may be appropriate to adjust the demand factor to account for the specific lighting requirements of the automated system. Fifthly, seasonal variations may be considered. Lighting needs may vary depending on the season. For example, during the winter months, warehouses may require more lighting due to shorter daylight hours. In this scenario, it may be appropriate to adjust the demand factor to account for the seasonal variations. Sixthly, the use of daylight harvesting can reduce load. If the warehouse utilizes daylight harvesting techniques to reduce the reliance on artificial lighting, the lighting load will be lower compared to a warehouse without daylight harvesting. In this scenario, it may be appropriate to decrease the demand factor to reflect the reduced lighting load. Seventhly, high bay lighting systems may require special attention. Warehouses with high bay lighting systems may have different lighting characteristics compared to warehouses with traditional lighting systems. In this scenario, it may be appropriate to adjust the demand factor to account for the specific characteristics of the high bay lighting system. Eighthly, the presence of skylights and windows matter. The presence of skylights and windows can affect the amount of natural light that enters the warehouse. This can reduce the reliance on artificial lighting and lower the lighting load. In this scenario, it may be appropriate to decrease the demand factor to reflect the reduced lighting load. Ninthly, regular maintenance and upgrades play a part. Regular maintenance and upgrades to the lighting system can improve its efficiency and reduce the lighting load. In this scenario, it may be appropriate to adjust the demand factor to reflect the improved efficiency of the lighting system. Tenthly, consultation with professionals can help decide on factors. Consulting with a qualified electrical engineer or lighting designer can help to determine the appropriate demand factors for specific warehouse scenarios. These professionals can provide valuable insights into the lighting needs of the warehouse and recommend the most appropriate demand factors based on the specific circumstances. By carefully considering these factors and consulting with qualified professionals, it is possible to adjust demand factors for specific warehouse scenarios to optimize the lighting load and reduce energy consumption.